You think the world around you is real. The chair you're sitting in, the walls of the room, your own body, they exist. They're made of atoms, solid, tangible, measurable. But I'm going to tell you something that will change how you see everything. None of it is real, not in the way you think, not fundamentally. The objects around you, the particles they're made of, even the space containing them, are not real things. They're descriptions, approximations, useful fictions that work at your scale but dissolve when you look closely enough. I know that sounds insane, like I've lost my mind, but I haven't. I've spent 50 years doing calculations, working through equations, following logic wherever it leads, and it leads here, to the conclusion that reality as we experience it is not fundamental. It's emergent, constructed, a high-level summary of something far stranger underneath. Let me start with something simple, a table. You see a solid brown wooden table. You can touch it, knock on it. It resists your hand. That resistance feels like proof of reality. The table is definitely there, except it's not. Not really. Zoom in. The wood is made of cells. The cells are made of molecules, cellulose, lignin, complex organic compounds. Zoom in further. Molecules are made of atoms, carbon, hydrogen, oxygen, but atoms are mostly empty space. The nucleus is tiny. The electrons are even tinier. If an atom were the size of a football stadium, the nucleus would be a grain of sand at the center, and the electrons would be specks orbiting at the walls. So the table is almost entirely empty space. What you're touching when you press on it isn't solid matter, it's electromagnetic forces. Electrons in your hand repelling electrons in the table. The sensation of solidity is force, not substance. Already the table is less real than you thought. But keep going. What is an electron? For a long time we thought it was a tiny particle, a little sphere of charge, but quantum mechanics says no. An electron isn't located at a point. It's spread out. It exists in a superposition of positions until you measure it. And when you measure it, you don't find where it was. You force it to choose a location. So the electron isn't a thing with a position, it's a probability distribution, a mathematical object describing where you might find it if you look. And what's more strange, the electron doesn't have definite properties until you measure them, its spin, its momentum. These aren't hidden variables waiting to be revealed. They don't exist until measurement creates them. This has been tested thousands of times. Bell's theorem proves it. Quantum entanglement experiments confirm it. The properties of particles are not real in the sense of existing independently of observation. They're contextual, relational. They emerge from interaction. Now you might say, okay, electrons are weird, but surely the table as a whole is real. It's made of many electrons and nuclei arranged in a stable structure. That structure exists, whether I observe it or not. Does it? What makes you think that? You've never observed the table when you weren't observing it. That sounds like a joke, but it's a serious point. All your evidence that the table exists comes from interactions. Light bouncing off it into your eyes, forces from it pushing on your hand. When you're not interacting with the table, you have no evidence it exists. Quantum mechanics suggests it might not as a definite configuration of particles. The table exists in a superposition of many possible configurations until something measures it. And measurement doesn't reveal which configuration was real. It creates a definite configuration from the superposition. Most physicists don't like this interpretation. They prefer to think the table has definite properties we just don't know about until we measure. But that's not what the equations say. The equations say the table is in a superposition, and experiments on quantum systems prove that superpositions are real, interference patterns, quantum computers. These things only work because superpositions are physical, not just descriptions of our ignorance. So the table isn't real in the classical sense. It's a quantum object, and quantum objects don't have definite properties independent of measurement. But it gets worse. Not only are objects not real in the way you think, the space they occupy isn't real either. I've talked about this before, but it's worth repeating because it's so important. Space is not a container, not a stage, not a pre-existing framework where objects live. Space is a relationship, a pattern of correlations between quantum states. When we say two objects are 1 meter apart, we're describing how they can interact, what signals can pass between them, how their quantum states are entangled. Distance emerges from information. Geometry emerges from entanglement. And if space is emergent, then objects in space are doubly unreal. They're quantum superpositions existing in an emergent geometry. Neither the objects nor the space are fundamental. Both are high-level descriptions of quantum information organized in particular ways. What about time? Surely time is real. Events happen, things change. There's a past and a future. You remember yesterday. You anticipate tomorrow. Time must exist. But time is even stranger than space. In classical physics, time was absolute, a universal clock ticking away independently of everything else. Einstein destroyed that picture. Special relativity shows that different observers disagree about simultaneity. What you call now someone moving relative to you calls past or future. There's no universal present moment. General relativity goes further. It shows that time flows at different rates depending on gravity. Clocks on GPS satellites tick faster than clocks on Earth's surface, not because the satellites have better clocks, but because time itself runs differently. Space-time is a unified four-dimensional structure. You can't separate space from time cleanly. And then quantum mechanics enters. In quantum gravity, there's no absolute time. The Wheeler-DeWitt equation, which tries to describe the quantum state of the universe, doesn't have time in it at all. It's a timeless equation. Change emerges from correlations between different parts of the quantum state. Some physicists think this means time is an illusion, that at the fundamental level nothing changes. Everything just is. What we call time is our experience of moving through a static four-dimensional structure, like playing a movie. The whole movie exists on the film. Playing it creates the illusion of time passing, but nothing is actually changing. All the frames exist simultaneously. I don't fully accept that view, but it might be partially correct. Time as we experience it, as a flowing river carrying us from past to future, is probably not fundamental. It emerges from thermodynamics, from entropy increasing, from the particular way we as subsystems of the universe interact with the rest of it. So objects aren't real, space isn't real, time isn't real. What's left, you might say, consciousness. Surely the fact that you're experiencing something is real. That's the one thing you can't doubt, the direct experience itself. Descartes said this, "I think, therefore I am." Even if everything else is illusion, the thinking itself is real. And maybe that's true. But what is thinking? What is consciousness? We don't know. Neuroscience shows it correlates with brain activity, patterns of neural firing. But we don't understand how physical processes create subjective experience. Some people think consciousness is fundamental, that it's the only real thing and matter emerges from it. But I don't see evidence for that. Consciousness seems to be what brains do. Complex information processing creates the experience of being someone. Damage the brain and consciousness changes. Destroy the brain and consciousness stops. So consciousness is probably emergent too. It arises from physical processes, and those physical processes are quantum mechanics, which means consciousness emerges from the same quantum information that gives rise to space and time and matter. It's all part of one structure. Nothing is privileged. Nothing is more fundamental except the quantum state itself. And here's the truly disturbing conclusion. The quantum state might not be real either. Not as a physical object, it's a mathematical description, a way of encoding what we can predict about measurements. Different observers might use different quantum states to describe the same situation. like different coordinate systems describing the same geometry. This is called the relational interpretation of quantum mechanics. It says the quantum state is relative to the observer. There's no absolute quantum state of the universe, just different perspectives, different ways of dividing the total system into observed and observer. If that's true, then literally nothing is real in an absolute sense. Everything is relational, contextual, defined only in reference to something else. Objects exist relative to measurements. Space exists relative to interactions. Time exists relative to change. Even the quantum state exists relative to an observer. So, what is real? Is anything fundamental? The only thing I can point to is the mathematical structure itself, the rules, the relationships, the patterns. There's something abstract and mathematical underlying everything. And when you look at it from different perspectives, you get different descriptions. Objects, fields, particles, space, time, observers. But none of these is the reality. They're all views of the reality. Maps, not territory. Now you might be thinking this is just philosophy, word games. Of course, we can say nothing is real if we define real narrowly enough, but practically speaking, tables are real, atoms are real, space and time are real. They have measurable properties, they obey laws. Isn't that enough? Maybe. For everyday purposes, yes. You can live your whole life treating the world as real and you'll be fine. The emergent descriptions work, engineering works, medicine works, technology works. All of it assumes objects in space and time behaving according to laws. And those assumptions deliver results. But when you push to extremes, the descriptions break down at the Big Bang, inside black holes, at the Planck scale, in quantum computers. These are places where the emergent picture fails, where you need the fundamental description, and the fundamental description doesn't include the things you think are real. Let me give you an example. Particle physics. We've discovered dozens of particles, electrons, quarks, photons, neutrinos. We study their properties, their masses, their charges, their interactions. We've built the Standard Model, a complete theory of all known particles and forces, except gravity. But what is a particle? We used to think it was a little billiard ball, a localized object with definite properties. But that's not what quantum field theory says. Quantum field theory says particles are excitations in fields, and fields are mathematical objects defined at every point in space. An electron isn't a thing, it's a ripple in the electron field, but we just established that space isn't fundamental. So if fields are defined on space and space is emergent, then fields are emergent too. And if particles are excitations in fields, then particles are emergent. The Standard Model, everything we know about particle physics, is an effective theory. It works at certain scales, but it's not the deepest description. What is deeper? We don't know completely. String theory offers one picture. It says fundamental objects are strings, and different vibration patterns of strings appear as different particles. Electrons are one vibration, quarks are another. The Standard Model emerges from string dynamics, but even string theory might be emergent. It's defined in space-time, 10-dimensional space-time, but still space-time. And if space-time is emergent, then string theory is emergent. There might be something deeper still, some formulation that doesn't use space-time at all. Holography points in this direction. The holographic principle says that physics in a volume can be described by a theory on the boundary, and that boundary theory might not have space. It might be a quantum theory defined on an abstract Hilbert space with no geometric structure. Space and particles and strings all emerge from that when you coarse grain. If that's right, then literally nothing in physics as we currently understand it is fundamental. Particles are emergent, fields are emergent, space is emergent, even strings are emergent. What's fundamental is quantum information, abstract states and operations. And everything else is patterns in that information. This is why I say everything is not real, not to be provocative, not to deny that you have experiences or that the world behaves predictably, but to point out that what we call real, what we identify as existing, is always a description, a level of organization, a coarse graining of something deeper, and we don't know where it ends. We don't know if there's a bottom level. Maybe it's quantum information all the way down. Maybe quantum mechanics itself is emergent from something deeper. Maybe there's an infinite regress of descriptions, each more fundamental than the last. Or maybe the whole idea of fundamentalness is wrong. Maybe there's no bottom, just different descriptions at different scales, all equally valid. None more real than the others. Physics doesn't discover what's real. It discovers relationships between descriptions, how one level emerges from another, how different formulations relate. This is the view I'm leaning toward. That reality isn't a pyramid with fundamental stuff at the bottom and emergent stuff built on top. It's a web of descriptions, different languages for talking about the same underlying structure. And that structure isn't a thing. It's a pattern, a consistency condition. Whatever can be described coherently exists in some sense. But then what determines which descriptions we use? Why do we experience three-dimensional space instead of seven-dimensional space? Why particles instead of something else? The answer might be anthropic. We experience this description because we're the kind of subsystems that can only form in this description. Other descriptions might exist mathematically, but they don't support observers. That sounds circular. The universe has properties that support observers, because observers can only observe universes with those properties. But it might be the only answer we get. If there's a landscape of possible descriptions, a vast space of mathematical structures, then we necessarily find ourselves in one that supports our existence, just like you necessarily find yourself on a planet with breathable atmosphere, not because all planets have atmosphere, but because you couldn't exist on the ones that don't. String theory suggests this is true. The landscape of string vacua contains perhaps 10 to the 500 different solutions, different ways to compactify the extra dimensions. Each gives a different effective physics, different particles, different forces, different constants of nature, and we're in one of them, probably not a unique one, probably not special except that it allows observers like us. Most physicists hate this conclusion. They want uniqueness. They want to calculate the electron mass from first principles and get our value, not one of 10 to the 500 possible values. But nature doesn't care what we want, and all the evidence points toward a landscape, toward multiple possibilities, toward our physics being contingent, not necessary. If that's right, then even the laws of physics aren't real in an absolute sense. They're accidents, features of our particular vacuum. Other vacua have different laws. All of them are equally valid descriptions of different regions of the mathematical structure. So what is real? Nothing. And everything. Nothing is real in an absolute fundamental sense that exists independently of description. But everything is real as a description, as a pattern in the mathematical structure. Tables are real patterns. Electrons are real patterns. Space and time are real patterns. Even you are a real pattern, a particular organization of quantum information that experiences and thinks and asks what's real. The pattern is real even if it's emergent, even if it depends on how you divide up the system, even if other observers would describe it differently. Real doesn't mean fundamental, it means consistent, predictable, part of a coherent description. And here's what makes this bearable. Even though nothing is fundamentally real, the relationships between things are stable. The laws connecting different levels are precise. You can trust that the table will be there tomorrow because the pattern is stable. The quantum information organizing itself in that configuration is in a low energy state that persists. Physics isn't about finding what's real. It's about finding what's predictable, what patterns persist, what relationships hold. and those patterns and relationships are as real as anything gets. They're what we mean by real, even if they're not fundamental. This changes how I think about my work. I used to think physics was about discovering reality, peeling back layers to find what's underneath. But now I think it's about mapping relationships between descriptions, understanding how one level emerges from another, how different formulations connect, how the web of descriptions hangs together. And that web is beautiful. The fact that quantum field theory emerges from strings, that strings emerge from M theory, that geometry emerges from entanglement, that thermodynamics emerges from microscopic dynamics, that consciousness emerges from neural patterns. All of this fits together, not perfectly. We have gaps, but the overall structure is coherent. That coherence is the closest thing to real I can point to, not objects, not space, not time, not even quantum states, but the fact that there's a mathematical structure connecting all descriptions, that you can start from quantum information and derive geometry, or start from geometry and derive thermodynamics, or start from particles and derive chemistry and biology and thought. The structure is self-consistent. That's what makes it real. Not that it's made of something, not that it exists independently of us, but that it all fits together, that the different descriptions tell the same story, that mathematics constrains what's possible and nature chooses one of the possibilities, or maybe nature chooses all of them and we're in one. That's the many worlds interpretation. Every quantum measurement splits the universe into branches. Every possibility happens. We just experience one branch. All the others are equally real. I don't know if that's true, but it's consistent with the equations, and it eliminates the mystery of measurement. Nothing special happens when you observe. The universe just evolves, branching into different configurations. What feels like collapse, like the electron choosing a position, is just you and the electron becoming entangled. Different versions of you see different outcomes, all in the same mathematical structure. If many worlds is right, then literally everything possible is real. Every quantum event spawns universes where each outcome occurs. The set of all branches, the quantum multiverse, is the complete reality, and what we call real is just our particular branch, our slice through the mathematical structure. But even in many worlds, the structure itself is what's fundamental, not the branches, not the particles or fields or spaces in each branch, but the mathematical object containing all branches, the universal quantum state. And that state might be a description too, relative to some meta-observer, turtles all the way up and down. I've been thinking about this for 50 years and I still don't have a final answer. What is real? I don't know. Maybe the question is wrong. Maybe real is a category error. Maybe we should ask what's consistent or what's predictable or what's useful, but not what's real in some absolute sense. Because absolute doesn't seem to exist. Everything is relative. Everything is contextual. Everything is emergent from something else or gives rise to something else. There's no bottom and maybe no top, just different levels of description, all connected by mathematics. And if you find that unsatisfying, you're not alone. I find it unsatisfying too. I want there to be something solid, something fundamental, something I can point to and say that's real. But the more I learn, the less I find. Every answer raises deeper questions. Every foundation turns out to be built on something else. But maybe that's okay. Maybe the quest for ultimate reality was always misguided. Maybe what matters isn't what exists, but what we can predict, what we can calculate, what patterns we can find. And by that measure, physics is incredibly successful. We can predict particle collisions to incredible precision. We can calculate the orbit of planets. We can engineer quantum computers. We can build bridges and cure diseases and send spacecraft to other planets. All of it based on descriptions we know are approximate. All of it working despite nothing being fundamentally real. So when I say everything is not real, I don't mean nothing matters. I mean the opposite. What matters is the structure, the relationships, the patterns that persist even though the objects aren't fundamental. Reality is those patterns. And understanding them, mapping them, connecting them, that's what physics is about. Not finding what's real, but finding what's true about the patterns we observe. And those patterns, emergent as they are, approximate as they are, contextual as they are the only reality we have, the only reality we need, and the only reality that might exist.